Okay, so first we will do a revision of the last class and then we will continue. Okay, so we are at day 11 today. Okay, so what did we see in the last class? We saw how do we evaluate a classification problem. So we learned about a new set of supervised learning problems, which was classification. So supervised learning has two components. One is regression and one is classification. We saw one algorithm in regression, which was linear regression. This we have seen. Now we are looking at our first algorithm in classification, which is logistic. But before that, we learned how to evaluate any classification algorithm. Okay, so just like for regression you have MAPE, you have sum of squared error, you have RMSE, and you have R square. Now these apply to all regression models, not just linear regression. These apply to all regression models. Similarly, for classification, we have accuracy, we have sensitivity, we have specificity, we have precision, we have the error. So these apply to all classification algorithms, not just logistic regression. Okay. So we saw these in details. Let us discuss about that. So we saw that in a classification problem, our output is no longer a number. Our output is always a class. So it can be a yes or a no class, or a 1 or a 0. Okay. So our actual values are ones and zeros. And similarly, our predicted values will also be ones and zeros. The values that we predict will also be ones and zeros, or yes and no, you can say. We take 1 for a yes and 0 for a no. And then we prepare a table. We prepare a table called classification or confusion matrix. Okay. And then we count. We count how many data points fall in this box, how many data points fall in this box, and so on. And depending on that, we calculate our errors. So we saw in the last class that there are two words used to represent these. So quick recap, what are those two words, guys? First, which word should we look at? First, we should look at the second word. So there are two words in each of these. We should look at the second word first. And how do we decide that? What is the second word? Yeah, if it is 1, it means it is positive. But what if it is 1? 1 for actual or 1 for predicted? Which one are you telling me? Predicted, yeah. So if predicted value is 1, that means the second word is positive. So I will write positive here because the predicted value in this column is 1. Similarly, the predicted value in this column is 0. So I will write negative, negative. Now it is easy. Now all you have to do is just check whether it matches the left hand side and the column, the row name and the column name, whether they match or not. If they match, you write true. If they don't match, you write false. So these are the terms. If our actual value is 1 and you predict a 1 for it, we call it true positive. If our actual value is 1 but you predict a 0 for it, it is a false negative, and so on. Now using these values, we can compute the evaluation parameters. So the first evaluation parameter is accuracy. So this is a normal accuracy which pays equal weightage to both ones and zeros. Okay, we take both true positive and true negative here, so it gives equal weightage to both positives and negative. And you can see here both are with the same weight. I am giving equal weight to identifying a 1 correctly as well as equal weight to identifying a 0 correctly. So this is accuracy. And here we will have total. So by total I mean TP plus FN plus FP plus TN. So all of them, all four of them. So this is the accuracy. Similarly, we can compute the error. How many points are we not able to identify? So we saw that this one and this one, they are mismatches for us. Because in this case, actually it was 1, we were predicting a 0. Similarly, for this case, actually it was 0, we were predicting 1. So these two are errors for us. So when we compute the overall error of the model, we just add these two terms. So I will add FP plus Fn divided by total. Or I could have also written 1 minus accuracy. Both will give the same value. Now in the last class we saw that depending on your business scenario, you might want to give different weightage or only weightage to one of them. So depending on your business scenario, accuracy might not be important for you. So in some cases you will find only ones will be important for you. So we discussed the example of identifying a cancer patient. So in that case, identifying the ones is more important. Identifying the zeros is not important at all. So in these cases, we will not look at accuracy or error to evaluate the model. In these cases, we will look at other parameters which focuses only on ones. So one such parameter is sensitivity. So sensitivity is the true positive rate. So which only focuses on the positives. It does not focus on the zero. So the formula for this is also known as recall. The formula for this is true positive divided by the row total. Whichever row true positive appears, take that row total. So TP plus FN. So this is the formula for sensitivity. What does this tell you? This tells you that how many positives were you able to identify out of all actual positives. If you see this denominator, the denominator is these two, and these two are nothing but actual positives. These two are one actual one. So how many positives were you able to identify out of all actual positives? So let me write it down. Positives the model identified out of all actual ones or out of all actual positives. Now, when this is the case, what we can do is we can just predict all ones. We can predict all records are ones and we can get a very high value of sensitivity. But that model would not be useful because it is not even distinguishing between ones and zeros. So to keep a check on that, we have another parameter called precision. So this allows you to not just blindly predict a one. So precision is very similar to sensitivity. The formula is very similar. So it is true positive divided by column total this time. This time you will not take the row total, you will take the column total. So TP plus FP. So now in the denominator, if you see, the denominator is the predicted positive, not the actual positive, but the predicted positive. So these are in the denominator now, the column total. So if I have to write it down, how many were positive out of all predicted positive? Okay, or how many positives did the model identify out of all predicted positives. So this the difference is only here. Actual positive and predicted positive. That's the only difference between sensitivity and precision. Okay. So these are the parameters that are used to evaluate a classification model. Is that clear, guys? This is all that we covered last class. Yes, Nitish. That means out of what are you asking? You told something like 2 by 3 in precision. That means out of 3 true values are predicted correct, which means it is overfitting. What is overfitting? I have not taught you overfitting yet, so don't worry about it now. So don't worry about overfitting now. You will know when the time comes, okay? We will cover that today. So overfitting, we will talk about it today in today's class. Okay. So apart from this, what did we cover in the last class, guys? Do you remember? Variable concept did we cover in the last class? Linear regression assumptions, I think that should be clear, right? Because it was covered last week. So I don't want to jump to linear regression now. Okay, yeah, specificity. Yeah, so similar to this, there is another parameter called specificity also that is not popularly used. So specificity is false positive rate. Okay, it is false positive divided by the row total. So false positive divided by row total. So FP plus TN. Okay. Yes. So when we do modeling, yes, we check whether the dependent variable is normally distributed or not. Yes. Yes, that is an assumption. So let's discuss the assumptions quickly. Assumptions of linear regression. So what are the assumptions? The first is that dependent variable and independent variables should have a linear relationship. Okay. Dependent variable and independent variable should have a linear relationship. Now that doesn't mean that if you have a dependent variable income and if you have a independent variable gender, don't expect this to have a linear relationship because this is categorical. So it doesn't make sense. It will never have a linear relationship in this case. But if the independent variable is numerical, then it should have a linear relationship. Now, guys, these assumptions are not very hard assumptions, okay? These assumptions are we often run linear regression even though these assumptions are violated. So don't think that if it is not linear, I will not run linear regression. This only means that your output might not be very good if you still go ahead and run linear regression, which is what you saw in the case study, right? Your R square was around 40%, which is not good because the data was on violating almost all the assumptions. Okay, so this is one of the assumptions. The next assumption is dependent variable should be normally distributed. Okay. Now these two assumptions are often not the case. They are not valid in cases, which is why we do all the transformations. So taking the log or taking the square of a variable, sometimes the square root of the dependent variable. So all these are done because these assumptions are very strongly violated. So for example, in the case study you would have seen, without taking the log of the normally of the dependent variable, the the dependent variable looked something like this. After you take the log, it looks like a normal distribution, not perfectly a normal distribution, but more closer to a normal distribution. That is why we took a log, so that it becomes closer to the assumptions. This was a violation of assumption, but this is not so much a violation, even though this did not give you a perfect normally distributed curve. And you could have checked that. So without taking the log, run linear regression, see what r square you get. Again, take log and run linear regression, see what r square you get. You will see around 10% improvement, 0.1 improvement in r square as a result of this. Okay, so these two are assumptions. These two are the first two assumptions. Now other assumptions are, one assumption is of homoscedasticity. So next is that of homoscedasticity. What does this mean? This means that your errors should have a constant variation, should have a constant variance. Okay, and the other is that the errors should be normally distributed also. The errors should also be normally distributed, and that they should have a constant variance. And there is one more, errors should be random. There should not be any pattern in the errors. Okay, so all these three together is known as homoscedasticity. If they violate, it is heteroscedasticity. Okay, and there was one final assumption, which is there should not be any multicollinearity in your data. So these are the assumptions of linear regression. Yes, Pranay, you should take the anti-log at the end. If you are taking a log of the dependent variable, at the end you should make sure you are taking anti-log. Otherwise, the answers that you give will be log of the price of houses. For example, in the case study, if it was the losses due to somebody defaulting a loan, you will give him log of losses. You will not give him losses directly. So that would be useless for the person, right? For the bank, if you give them log of the losses, what will they do with that? They need the losses, not the log of losses. Amar, there is no rule there. You try different things and see which one gives the best accuracy. So when do you take a log? When do you take a square? It all depends on the scenario. There is no specific rule that if this is the case, you use log, or if this is the case, you use square. Okay, it all depends on the scenario. You apply all the three or whatever transformations you have and see which one converts it to a normally distribution curve. Yes, Tapan, that is what we saw in the last class, right? So the same thing you have to do. To check for homoscedasticity, you plot your errors with respect to the predicted values. So if these are your errors, you plot it with respect to predicted values to check these three. Okay. Okay. Next, coming to the p-values. what importance? So looking at the p-values, we decide which variables are significant. Okay, so p-values help us do feature selection. So feature is another word for column or variable. Now p-values help us do feature selection. That means it helps us decide which columns are important or which variables are important and which are not. So how do we decide? Whichever variable has the highest p-value, whichever variable has the highest p-value, if that is above 5%, of course, that means it is not significant. That means it is not significant, so we remove that variable. Okay, so we do that iteratively. We do that iteratively, one at a time. Okay, it's not that you have, let's say you have independent variable 1, independent variable 2 and 3, and the p values are, let's say, these are the p values. Okay, so you don't remove all of them together. You remove the first one, which is the highest p value. So you will remove this and then rerun your model taking these two, and then you will check the p values again. If it is still above 5%, then again you remove one of them, and then you proceed again. So you do that iteratively and not together. You don't remove all the three together. Okay, so that is the way to finally come up with the final model, which has all variables significant. So these were the topics that was covered in the last class. Okay, guys. So let us move ahead now. You want me to open the case study? At the end. So I am not sure why all of you are asking the same questions again. I told you very clearly, at the end you will take your anti-log. At the end, after all your modeling has been done, after you have selected your R square and everything, then at the end you will take your anti-log. So where are your predicted values now? Your predicted values are, in which variable have I kept them? Yeah, so pred has the predicted values. Pred is the variable which has the predicted values, but pred is in the form of log because we have taken the log. So whatever values you have in the pred are log of the losses, not the losses directly, but log of the losses. So at the end here you will take the anti-log of it at this point. At this point, define a new variable. Let's say predicted loss, and you take anti-log of pred. Yes. This is your final answer. This is what will go to the bank. I hope everybody knows how to take anti-log. Okay. If log of x to the base e is equal to y, how will you take anti-log in this case? How will you find x? How will you find X you will find by x is equal to e to the power y. So this is how you will take antilog. So whatever values you are getting after the model, just raise them to the power e, and you will have the original losses. So log of losses to the base e is equal to your pred variable. This is what you are predicting. Okay, you are predicting this, but you have to find this. So how will you find? Losses is equal to e to the power pred. This is your final answer. Okay, so that is all that we covered in the last class. Now let us start with logistic regression. Okay, before we start with logistic regression, let us discuss about overfitting. Now overfitting is not an algorithm, or overfitting is not a technique. Okay, this is a phenomenon which can happen in any algorithm. This is a phenomenon which can happen in any algorithm. It happens in logistic, linear, and all other algorithms that you will see. Okay, and this is often a problem. This is a big problem in machine learning models. So you have to take care that your models are not overfitting. Okay, we will see what happens as a result of overfitting. Why does it happen? And how do we avoid overfitting? So let me give you an example. Let's say we are trying to predict income with respect to age. And these are the data we have. Okay, this is the data that we have. Now I will run a model through it. So this is my model 1, the green model, and I will draw another model through it. This is my other model. Okay, so I have done two models through this data. One is the red model, which you can see it's a linear regression model, and the other is some other complex model I have run. Now which of these models is good? Which model will you prefer, and why? First tell me which models will you prefer, the green one or the red one? Tell me by the color, which is first and which is second, I don't know. Tell me by the color, the green one or the red one? Okay, so we are having almost 50-50 answers. So half of the people are saying green, half of the people are saying the red one. Okay, so people who said green, why do you think you will take the green? People who said red, rather. So people who said red, why do you think you will take the red one? So we all can identify that the red one has higher error, right? That is pretty clear to everybody. The red one has more error than the green one. The green one is passing through almost all the points. So the error for green one is almost zero. But the red one has some error. So the error for green one is zero. But the red one, it has some error. Okay. Okay. Yeah, fair. That's why I did not ask the green guys. So the people who said green one, I'm not asking you why did you choose the green one, because this is the reason why you chose green one. But people who chose red, I'm asking them, why did you choose the red even though you knew that it has higher error? Still you chose red one. Why? Because the answer is red one, by the way. I will also choose the red one, not the green one. So what, Pradeep? If the green one is deviating and red one is a nice straight line, so what? Yes, it is better for future. No, Pranay, not because it has a linear relationship. That doesn't mean it is better. Okay, Pranay. So you cannot say that I am selecting the red one because it is linear. The original function which is there between the two, it may not be linear. So it doesn't mean that it is better. But what Pradeep says is correct. It is better for future prediction. Okay. Now, why will the red line be better for future prediction? Let's see. Now, the disadvantage of the green one here is that for the green one, it will not do well on future data. Okay. It will not do well on future data. The green one. Because see, the shape is so complex. The shape is so complex that, let's say, in the future, we have points here. Okay, these are the points we will get in the future. Now you see the green one. Now the green one will start having higher error on the future data, but the red one will be more accurate on the future data. See the green one, it is going to this point only because there is a point here. In the future data there might not be a point somewhere here. Now right now it went up only because there was a point here. If if there was no point here, it would not have gone there. So it is overly complex. It is too complex. So it will not do well in the future data. But the red one will do. And remember, we discussed about the real test of a model. The real test of a model is how well it does on the test data. Okay, by future data, I mean the test data, the data on which the model is not trained. So the real test of a model is the test data, not the training data. Okay, not the training data. So in case of overfitting, what happens? The model performs very good on the training data, but on the test data it performs very poorly. That is the problem with overfitting. Any model you build, it will show you a very good accuracy on the training data, but on the test data it will not show you a good accuracy. So which is the answer to the question, if you guys had this question, that why are we calculating the accuracy twice, once on training data and once on test data? That is to check for overfitting. Because sometimes what happens, models they perform very good on the training data, but as soon as you go to the test data, they fail. So it's like the questions that you have memorized for the exam, you perform very well in those questions, but if some new question comes to you, you don't perform good in them. And that kind of a student is not a good student, right? He has just memorized the questions given to him before the exam, and this is exactly what a overfit model does. It just memorizes the points which has been given for training, but on the test data it fails because the test data points are new points, the points which the model did not see before. Okay, so that is why here the green one will not be good. I will prefer the red one, because the red one, though simple model, it will generalize well on the new data. Okay, so this is what is told. It will generalize well on the new data, whereas the green one may not generalize well on the new data points. So the definition for overfitting, let me write it down. Okay, so this is the definition of overfitting. When a model performs well on training data but does not perform equally well on test data, that is where the model has overfit. Yeah, this is the answer, Pranay. You anyways check the accuracy of both training and test. So let's say you got a R square of training is more than the R square of test. That means your model is overfitting. Okay. Or when your MAPE or RMSE or SSE of train is less than MAPE, RMSE or SSE of test. So whenever these two or any of the two is true, that means your model has overfit. Now this doesn't mean that if your training R square is, let's say, 0.80 and your test R square is 0.78, this doesn't mean that it is overfitting. This is minor difference. Okay, so plus minus, let's say, up to 6% is okay. Okay, this is random variation. This much is okay, but it should not be more than this. So if you have this as 80% and if you have this as, let's say, 72% or 72 to 73%, then this is okay. This is random variation. This is not a variation to conclude that the model has overfit. But let's say if this is 80 and this is 70, that means that your model has overfit. Okay, this means that your model has overfit, but not this. This is 73, so 7% variation. Maybe 7% it is right at the threshold. So maybe. But if the difference is up to 6%, it is okay. Up to 6% means it is random variation. You cannot conclude that it has overfit. But if the difference is more than 6%, if your training data accuracy is 6% more than the test data accuracy, that means that your model has probably overfit. Okay, 6% or more than 6%. So 80 and let's say 73, that means your model has overfit. So that is why this is one of the reasons we split the data into two parts and we check the accuracy of the model on both training data and the test data to check for any overfitting. Okay, and opposite of this is underfitting. Opposite of this is underfitting. Underfit means when your model is very simple. So in this case, our model was complex, right? The green one was overly complex. It was too complex. We don't need such a complex model because it will not generalize well. It will not generalize well on the future data. Okay. So similarly, there is underfit model, which is opposite of this, where your model is too simple. Okay. When your model is too simple, it doesn't perform well on both training and test. In this case, it will not perform well on both training and test. Okay. So for example, can you give me an example of underfit model, guys? You already know it. Can you give me an example of a underfit model which is too simple? Bank. Yes, the baseline model. Shubham is right. Okay, we have seen that, right? The baseline model which always predicts the average, that is also a model, right? So the baseline model is a model which is overly simple. It is too simple. Okay, that is the simplest model one can build, which always predicts the average. Okay, so this is an underfit model. So a baseline model does not perform well either on training or on test. We just use it as a benchmark. Okay, we just use it as a benchmark to compare our ML models. Okay, Okay, so that was the theory on overfitting. But let me give you another example to help you understand that. Now let's say this is your home. This is your home, and let's say this is your office. And you take this path from home to office. Okay, you take this path from your home to office every day. Now let's say it is a Wednesday. It is Wednesday today and it rained a lot. Okay, it rained a lot and there was some water here. There was some water logging here. So what you did not take this path. You took an alternate route. You took an alternate route. You went from here and then you took a detour and then you arrived here to your office. Okay, on a Wednesday it rained and this is what happened. Now if your model is overfitting, let's say you have a model which gives you the route. Okay, now what would happen as a result of this? The model will memorize that Wednesday on Wednesday he takes this route, and whenever next Wednesday comes, the model will start telling you that you should take this route because last Wednesday you took this route. So this is overfitting, and this is why it does not perform well. It does not generalize well because it not only captured that it rained, but it also captured that it is Wednesday. But this was not required. It took an additional variable which was not required at all because the rain had nothing to do with Wednesday. It just rained that day, and that is why you took that path. The next Wednesday it will not rain, or it might not rain, but the model will suggest you to take this route on every Wednesday. So the model is overly complex. So this is why this kind of a model does not perform well on the future data, or it does not generalize well on new data points because it has identified too many variables as influencing the model. So those variables might not be important for the model at all. Okay, now let us see, when does overfitting happen in linear regression or in logistic also. This will apply for logistic also. So when will overfitting happen in linear or logistic regression? This happens, you saw the example already, when you take too many independent variables. So overfitting in linear and logistic, it happens when you take too many independent variables. So you take variables which are not required. So now you know why you have to remove variables which are having higher p-values. Because if you include them, it will result in overfitting. So you will have to make sure that only those variables are in the model which have a less than 5% p-value. Because if any variable has more than 5% p-value, or any insignificant variable you have in your model, it will result in overfitting. So you should get rid of them. Okay, so if I have to draw, so in this example what did we see? The day of the week was a variable which was not required. Rain was good, we should have taken rain, because in the next week if it rains again you will take the same route, same alternate route you will take, but not on a Wednesday. So Wednesday was an insignificant variable. The day of the week was not required for this problem. Day of the week was an insignificant variable which you should not have taken. But since you took that, your model overfit. Your model overfit, and every Wednesday it started predicting that route, which was wrong. So to avoid this, you could have just dropped the Wednesday variable or the day of the week variable. You could have just dropped it. But if you drop rain again, the model will not work. Okay, so this is a trade-off. There is a trade-off between overfitting and underfitting. You cannot go on either side. Now imagine if you drop rain also. If you drop both day of the week and rain, then the model will always predict you a straight path even if it rains. Okay, so you will have to consider rain but not day of the week. So that is the problem with overfitting. It is a trade-off. It is a trade-off. So you have to be somewhere in the middle. One side you have overfitting, one side you have underfitting. Okay, now you will ask, how do we decide which side we are going on? You keep checking your accuracy on train versus the test. You keep checking for different models iteratively. You keep checking, and then you will know that okay, you have arrived at a point where if you go this side, your model is going bad. If you go that side, again your model is going bad. So that means you have to be where you are right now. Okay, and how do we have overfitting in linear or logistic regression? It has to do with the number of independent variables you use. Okay, number of independent variables used, and let's say this is accuracy. This is accuracy and this is the number of independent variables used. If you use too many independent variables, we saw right now, we used day of the week and it resulted into overfitting. So this side you have overfitting. Okay, when you use too many independent variables, and this side you have underfitting when you use too few independent variables. So either side you should avoid. You should be somewhere in the middle. So now let us draw the chart. Now overfitting is a problem just for the test data. For the training data it is not much of a problem. Okay, so for the training data you will see that the graph will be something like this. Okay, initially if you take very few variables, obviously accuracy will be low. This is for training data. Your accuracy will be low if you take very few variables. So very few variables means you have not taken the important variables also. So obviously accuracy will be low if you take very few variables. And as you increase the number of variables, your more important variables keep coming in and your accuracy improves. But after a point, the accuracy will not change because you have already added all the important variables, and now whatever you are adding is not important. They are just some junk variables you are going on adding here. So the accuracy will almost remain same. It might decrease slightly, but it will almost remain same. This is for the train data. But for the test data, you will see the overfitting pattern in test data. So in test data, what will happen? Initially, when your independent variables are too few, obviously you will have a less accuracy because you are taking very less independent variables or very few independent variables. It will increase as you go on adding variables. It will increase, but after a point, the model will start to overfit and the accuracy will start coming down. So this is how it will look like for test data. Okay. So remember the example which we saw in the previous page, the green model and the red model. The green model was performing good on the training data. Okay, always remember that is why some of you chose the green model because it had almost zero error. But we said that it will not perform good on future data. Okay, so that is why the blue graph here, I'm drawing it. It constantly rises because on the training data it will always be good. It will not You will not see the error on the training data. You will only see the error once you go to the test data, which is why it falls only for the test data, not for the training data. So if you compute the R square for both, you will know that okay, you are in this region or you are in this region. So you will have to iteratively do a few iterations and finally select this. This is where you should be. Oops. So this is where the best area. Okay. Did you follow this, guys? Take a moment and understand this. No, Prashant. Best is not the point where both curves meet. Now, what I have drawn is a generalized curve. They might meet here also. They might meet at this point also, but this means that it is overfitting. So the best point is where beyond which if you go, the test data starts to fall, but the train data remains the same. That is the best point. Okay. Now this is a generalized graph that I have drawn. There might be small variations here. Okay. So the green one might look like this. Similarly, the blue one might look like this. I have just drawn a generalized smooth curve for them. So the best is this area where if you go this side, both of them fall. If you go this side, the test data accuracy falls. That is the best area. Okay, so if you have understood this, now answer my question. I have number of independent variables here and I have map here. How will it look like now? How will the graph look like for training data? And how will the graph look like for test data? First tell me for training data, how will the graph look like? Tell me guys if you understood the previous graph. Straight, what does straight mean? This one, like this, or like this? Slope is equal to 1. Right skewed. So don't say a pure line, say a graph like this, right? This is what you meant, Pradeep? Okay. So this is what he says for our training data. What do you guys say? Yes, guys. What do others think? Increasing and then constant. Yeah, that's what I have done. It is increasing and then it is constant. So this is what you are telling for training data, right? Right, guys, Pradeep and Kandar? Okay, so everybody says this. Okay, so let's say I'm at this point. I'm using very few independent variables. So is it overfitting or is it underfitting? When I'm using very few independent variables, is this overfitting or is this under? This is underfitting, right? So you are saying at underfitting my error will be the smallest when I'm underfitting? Is that what you are telling me? That when my model is underfitting, my error will be the smallest. Is that correct? That means I should always use the baseline model because the baseline model is the most underfit model. So the baseline model will have the smallest error, right? This is what you are telling. So this is wrong. Okay, it will not be like this. If you draw it like this, that means you should always select a underfit model, but that is not the case. Okay, so this is wrong. So where should it be then? Then how should the graph be? It will be like this. Okay, it is opposite of that. So whatever I have drawn for accuracy, for error it will be opposite of that. Okay, so this is how the graph will be. If you are taking too few variables, your model is underfit. If your model is underfit, your error will be high. And as you go on adding more and more variables, your model becomes more and more accurate. And after some point, it will start to overfit. But overfitting is not really a problem for training data. So it will just stay constant. It will not decrease. It will stay the same. Okay. So this is how it will look like for training data. Now tell me for test data. For test data, how will it look like? Yeah. So it will look like this. Okay. Initially, the error will be high because your model is on underfit. It's a very simple model, so the error will be high. As you go on adding variables, the error will become small and small. And after some point, the model will start to overfit. And for the test data, overfitting is a problem. So if you go on adding more independent variables, the error will start to rise again. The error will increase again, and it will look like this. So this is how it will look like with respect to any of the error parameters, not just MAPE. Even if I had asked RMSE or SSE, it would look the same. Now you see both the graphs, they are inverse of each other. I have just inverted them because these two things work in inverse relation, right? Accuracy and error. If accuracy is high, error will be less. Accuracy is low, error will be high. So I have just inverted them. This inverted U becomes a straight U. Okay, and this was a increasing curve, it becomes a decreasing curve. So I have just taken a mirror image of them. So remember this, guys. This is asked in interview. Okay, so overfitting is a very commonly asked question in interview, and overfitting can happen in any algorithm. And by the way, whatever we are discussing now is true for logistic regression also. So logistic and linear, for both it is true. For other algorithms, we will see how does overfitting happen there. But for logistic and linear, this is the case. This is how overfitting happens. They happen with respect to how many independent variables you are using in your model. If you use too many independent variables, you will have a overfit model. If you use too few independent variables, you will have an underfit model. So you have to be somewhere in the middle. Okay, now let us start logistic. So now you have seen what is overfitting, what is underfitting. So you should take care of that while you are running a linear regression model or even a logistic regression. Now we can start with logistic regression. You guys want a break before we start this? Let's take a break. Okay, we'll take a short break. We will take a short break. We'll take 2 breaks today. We have a 4-hour class. So Okay, so now we have seen that for a classification case, our output, our dependent variable can take just two values, which is ones and zeros. Okay, our dependent variable can take only two values, ones and zeros. So the first question that you will ask, or that you will have, is why do we have a separate modeling technique for that? Why don't we just use a linear regression? Why don't we use a linear regression and predict the ones and zeros? Now the answer to that is, now your dependent variable is only 1 and 0. Okay. Whenever you draw a linear regression is like an infinite line. Okay, which has the range from minus infinity to plus infinity. This line has a range of minus infinity to plus infinity depending on the values of x that you give. But in the case of a logistic regression, or in case of classification, what we see is that our dependent variable can take only two values, 1 and 0. So going by linear regression will not make sense, because it can give you any value. It can give you 5, 10, minus 15, anything. But what you need is 1 and 0, not any other value. So how will you convert these other values to 1 and 0? That will be a question. So that is one reason why linear regression is not used for such problems where you have just 1 and 0 as the output. The other reason is that one of the assumptions of linear regression is that your dependent variable and independent variable should have a linear relationship. Okay, but again, in this case, in case of a classification, it is not possible to have a linear relationship between dependent and independent, because your dependent will always be either on this line, which is 1, or on this line. So your dependent variable will always lie here. Okay, with respect to your independent variable, your dependent will always be either 0 or 1 if this is your dependent variable y. So how will you prove this? Because it is not possible. Okay, so these are the reasons why you cannot use linear regression to solve such problems. Okay, okay, so these are the reasons why we cannot use the same linear regression model to predict in cases where the dependent variable is a category, where the dependent variable is categorical or quantitative. Okay, now let's come to logistic regression. So what do we do? So we cannot use a linear regression in this case, because the output of linear regression can be any number, any positive number or any negative number. It can be any number between minus infinity to plus infinity, depending on the values of x. But so what we do is, in logistic regression, what we do, we apply a function. We apply a function on top of linear regression. Okay, so g is a function that we are applying on top of linear regression, so that the output is always between 0 and 1. Okay, so we don't do any fancy stuff here. We just take the same linear regression line. We take the linear regression line. So the same line we will be taking, and on top of that we will apply another function. Let's say g, a function g we will apply on top of that, so that the output of the linear regression line is always between 0 and 1. So this is what is done in linear regression, in logistic regression. Okay, now what is that function? Let us see. Now that function g is known as logistic response function. Okay, so that function is known as logistic response function. Let's see what that function is. So after you apply that function to the linear regression line, what you get is this. You get a probability as the answer. That is the whole intention of applying that function, so that the output is between 0 and 1, and probability is always between 0 and 1. So the output of that function will be a probability, and that will be the probability of y is equal to 1, not y is equal to 0. Okay, it is the probability of y is equal to 1. Once you have this, you can easily find the probability of y is equal to 0, because the sum of the two is 1. You all know that total probability is always 1. So if you want to find probability of y is equal to 0, you just do 1 minus probability of y is equal to 1. But in the original equation, this is the probability. Now how does it look like? The logistic response function looks like this. So don't get scared. It's very simple. So this is the logistic response function. So if you see, we have just applied a few extra things to the function. It is the same. This is the same linear regression line. This is the linear regression line. We have applied a function on top of that, so that the output is always between 0 and 1. Now whatever values of x you take, your output will always be between 0 and 1. Okay, so if I represent theta as the linear regression line, then your logistic response function will look like this. Is the logistic response function 1 plus e to the power minus theta, where theta is the linear regression line. Now I said that the output of this will always be between 0 and 1. Let us prove that. Let us prove that the output of this will always be between 0 and 1. So to prove that, let us take extreme values of x. Okay, so let's say my x is infinity. That is the most positive value x can take. So if my x is infinity, let's say x is infinity. If it is infinity, what will be my probability of y is equal to 1? I will write 1 plus e to the power minus. If x is infinity, whatever you multiply with this and then add with this, it will always be infinity. So I'll get infinity here. So 1 plus 1 by e to the power infinity. 1 by infinity is 0. If you multiply 1 by a very large number, it will give you 0. So that means 1 plus 0, it is equal to 1. So that means if you take x as infinity, which is the highest extreme, what you get is 1. Similarly, if you take x as minus infinity, let's see what happens now. This is the most negative extreme you can go. You cannot go beyond that. So you will get 1 plus e to the power infinity. Now e to the power infinity is infinity, which gives you 1 divided by infinity, which is 0. If you divide 1 by a very large number, you get 0. So that means whatever values of x you take, you will always be between these. We checked with the extreme values, so you will never go outside 0 or 1. So this is what we intended. The whole purpose of applying that complex function g, or the logistic response function on linear regression, was this, and we have achieved that purpose. Okay, so now whatever we get will be a probability between 0 and 1. Do you understand that, guys? Guys, can you reply something in the chat? Okay. So Shalia, you just take extreme values and see what you get. So that's what I have done here. I have taken the extreme values. So in this equation, the extreme value of x that you can take is minus infinity and plus infinity. So I just proved by taking minus infinity and plus infinity that whatever left hand side you get is always between 0 and 1. Because whatever values you will get will always be between minus infinity and plus infinity. You will never get something beyond that. So even if you take minus infinity or even if you take plus infinity, what you get is always between 0 and 1. So this proves that applying the logistic response function on a linear regression line gives you a probability. It will not give you something outside of 0 or 1. So here is the proof. Okay, so this is how you run logistic regression. It is the same. So this is the maths behind it. Now there is another concept. Now how does this look like in a graph? Let us draw the graph for this. So if you draw the graph for this, it will look like a S curve. It is also known as S curve. Okay, it looks like a S here. It is also known as S curve, where on the x-axis you have the probability, on the y-axis, sorry, on the y-axis you have probability, and on the x-axis you have your linear regression line. So remember this, guys. Okay, this is how the curve looks like. Oops, one sec, let me draw it again. This is probability of y is equal to 1, and your x-axis is the linear regression line. Okay, so this is also known as S curve. Now remember what is on the y-axis and what is on the x-axis. Okay, don't forget this. Just remembering the graph is very easy. It is a S curve, we all will remember. But also remember what is on the x-axis and what is on the y-axis. That is where people get confused. This is the linear regression line, or theta, and this is what is on the left hand side. The probability of y is equal to 1. Now there is a concept of odds in logistic regression. Okay, there is a concept of odds. So what is odds? So odds by definition is probability of y is equal to 1 divided by probability of y is equal to 0. This is the definition of odds. Okay, This is the definition of odds. It means probability of y is equal to 1 divided by probability of y is equal to 0. So now we can convert this to 1 minus probability of, so I can write this, and now I can bring the logistic regression graph curve here. I can bring the equation of logistic regression here. I know what is probability of y is equal to 1 as per logistic regression curve. So if you do this, guys, if you bring that curve here, and if you do the calculation, what you will get is this. So I'm directly doing it instead of showing you the calculation. You will get this as the output after you solve it. Okay, you will get this. Odds is equal to e to the power theta. Now I can take log of this. If I take log of this, so if I take log of this, log to the base e, log e will become 1, and I will get a linear regression line. Log of odds is also known as logit. Log of odds is also known as logit. So this gives us logit is equal to beta naught plus beta 1 x1 plus beta n xn. So this is the final equation. Okay, this is why one of the assumptions of logistic regression, now I'm covering the assumption of logistic regression. There are just two assumptions. One is that logit and the independent variables should have a linear relationship. And you can see here, right, the logit that you have and these x1, they have a linear relationship. It is no longer y here. Okay, instead of y we have logit. What is logit? Logit is log of odds. So logit and the independent variable should have a linear relationship. That is the assumption in logistic regression. And the other assumption is no multicollinearity. That remains the same. Okay. The other assumption is no multicollinearity should be there even in logistic regression. So these are the only two assumptions that you have in logistic regression. Okay, one is that your log of odds and your independent variable should have a linear relationship, and the other is that there should not be any multicollinearity. Yes, log is just a term, Nitesh. Log is just a term which is used. So log is very popularly used in English speaking countries, so especially in horse racing and all. They use this as very popular term. Just like we Indians use probability, they use odds a lot, which is why they converted it to a odds format also. So odds is equal to probability of y is equal to 1 divided by probability of y is equal to 0. And after that you deduce this. So finally you have logit is equal to the linear regression line, or log of odds is also known as logit. Okay, so this is all the theory on logistic regression. It's pretty simple. So you will just have to remember this equation. You will have to remember this one, and if you remember this log of odds formula, the formula for odds is pretty simple, that you will remember anyways. Odds, log of odds is equal to probability of y divided by probability of 1 divided by probability of 0. And then if you put this equation there, what you will get is log of odds is equal to the linear regression line. Okay. Now just like you have ordinary least square, remember you have ordinary least square in linear regression, which basically tries to minimize the sum of squared error, and in that process you get your betas, right? Similarly, in logistic regression also you have maximum likelihood estimate. You have a function which is known as maximum likelihood estimate, MLE. So what this does is it starts with random values of beta. It starts with random values of beta. So it will take random beta naught, beta 1 and so on. Okay, and then it will check whatever y you are getting, is it matching with the actual? Is the y matching with actual? If it is not matching, it will change the values of beta and repeat. Okay, and finally it will come up with the betas. It will come up with the betas when y is closest to actual. So this is how it finds the coefficients, the betas, okay, by using maximum likelihood estimate. Now you don't have to go beyond this, it gets very complex beyond this, but what it does, just like ordinary least square, here also you have a function which is known as maximum likelihood estimate. What this does is it starts with random values of betas, and using those random values it tries to predict your y, and then compares your y with the actual values. If it is matching with the actual values, then it stays with those same betas. But if it is not matching, obviously it will not match since it started with random values. So it will change the values of betas again. And then it will again check whether the prediction is matching with the actuals or not. Okay, so a lot of iteration goes on, and then finally you have your betas, which gives the closest output. So it is a very iterative process, and that is one of the reasons why it is very difficult to do logistic regression by hand. You cannot do a logistic regression by hand. You need a computer to do this because a lot of iterations are involved. Linear regression can be done by hand. You can create a line which gives the least sum of squared error, and we saw some examples also. So when we started with linear regression, if you remember, we saw some 3 lines, and we proved why one of the lines was better than the other. We did it by hand manually, but in logistic that is not possible, or very difficult. You cannot do it by hand because a lot of iterations goes on. Okay, so remember this maximum likelihood estimate. This is also asked in interviews. How does it decide the value of betas? So this is the answer for that. How much loss will a bank incur if a customer does not repay the loans? That was what you predicted in the first case study. In the second case study, which I'll send you, what you will do is, even before the customer results in a loss, you will try to predict whether a customer will default. So yes or a no. So that will be credit risk default. That is what almost all banks work on. They try to predict in advance whether a customer will not repay their loans. Okay, how much losses will they incur, that will come separate, but first we predict whether a customer will not pay his loans or not. Okay, or what probability exists for a customer to not repay his loans. So that is known as credit risk default, which will be the second case study. Shubham, it depends. You cannot say that which algorithm is most widely used. It depends totally on the scenario. Totally on the scenario and the requirements. So don't worry about this now. You will know this by the end of the course. Okay, so this is all about logistic regression. Yes, Vijay Mallya was an exception. Okay, Shubham, you can always go to Kaggle and start working. So there are hundreds of examples on Kaggle. Whatever I gave you is what I thought given the time that you guys have. I don't think you will have more time beyond that. If you start, somebody has turned on his mic. It is Arjun. Okay, I turned him off. Okay, so pre-processing of data, don't worry a lot about this, Shubham. I know it is very important, but from an interview perspective, it is not so important. So whatever I have given you, I think should be enough for you. If you have completed the Titanic assignment which I sent you, that should be enough. So you can focus more on the modeling part because this is what is asked in interviews. Okay. And of course, if you wish, you have websites like Kaggle. You go to Kaggle, there are many competitions there. You take Titanic competition, for example, there, and you work on pre-processing the data. You haven't learned all of the modeling techniques, so you cannot do much there. But you can take the data and do pre-processing there. Okay. And whatever homeworks I am sending out, that does require some pre-processing. So anyways, that is helping you practice. I hope, Shubham, you have completed all the assignments which I have sent so far. Okay, so yeah, so that is how logistic regression works. Now, remember the baseline model that we talked about in regression? What was the baseline model? We talked about baseline models, right? What was it? Yeah, a baseline model in regression always predicts the average. Now, similarly, we have a baseline model in classification also. In classification also we have a baseline model. But here taking the average will not make sense because we have just ones and zeros. So what should we take as the baseline model? What do you think, guys? What should we take as the baseline model? Always zero? Why always zero? Why not always one? Yeah, but why not one? Yeah, so what we do is we take the mode. We take the mode, which means whichever is more in proportion. If 1 is more in proportion, we take 1. If 0 is more in proportion, we take 0. This is the baseline model in classification. Okay, in regression, we take the average. In classification, we take the mode. Okay. So let me give you one example then. So I hope everybody has their notebooks open. Okay. So this is a data that you have. Okay. This is the data that you have. Now you have to find me the accuracy, then the error, then the sensitivity, specificity, and precision. You have to find me all these parameters for a baseline model. Guys, is the video not working properly? Okay, I am not sure why then. So you'll have to find me these things for a baseline model. Okay. So this is what you have to do. So find all these parameters for a baseline model. And this is the data that you have. Okay. So use your notebooks and do this. I'll wait for 2 minutes. Sorry guys, I had paused my screen. I thought my screen was moving. I had paused my screen initially, so it was at the same place. The video was not stuck. I just checked now. I was looking at this Excel. I was looking at this Excel to see what things I have planned. And I had the logistic response curve on the screen. So I thought I'll allow you guys to look at the equation, and meanwhile I'll look at this. So I had paused my screen and I forgot to unpause it. Okay, but this is how it is. Okay. Oh, did you guys see this MLE when we discussed maximum likelihood estimate? Was the screen available when we saw this? Okay. Okay, then we did not cover a lot after this. I just told you that about a baseline model. In a baseline model in regression, we take the average. Okay, we take the average as I have written here. For a classification, we take the mode, because we don't know which one will be more. Will zeros be more or will ones be more in the data? Whichever is more in proportion, we predict that. We predict that for all the records. Okay. And now the task for you is that this is the actual data given to you. These are the 10 rows. These are the actual values. You have to find me these parameters. Okay. You have to find me these parameters for a baseline model. So do this and tell me the answer. So accuracy is 60%. Error is 40%, sensitivity 0%, specificity 100%, and precision is. Anybody else got the answer and got the same answer as Prashant? Okay, did you get the same answer, Nitish? Did others get the same answer as him? Okay, yeah, that is correct. So what you will do in this case is simple. You will just add a predicted column. So actual column is given to you. You just add a predicted column. Okay, I'll add my prediction. And prediction will always be 0. So remember, we are talking about a baseline model here. A baseline model is a model which predicts the mode. So what is the mode here? If you see how many ones are there in the data and how many zeros are there in the data, there are 4 ones in the data and there are 6 zeros. So that means the mode is 0. So the baseline model will always predict 0 irrespective of what the actual value is. The baseline model will always predict 0. So let me write 0 for all the rows. I will write 0. Okay, so now I have my actual value, I have my predicted value. Now you should know how to calculate. Just compute the confusion matrix and then compute the parameters. So you can write 1 0, this is for actual. You can write 1 0, this is for predicted. You can draw the table. So how many are actual ones and you are predicting ones? So notice a baseline model is not predicting any one. So this entire column I can make it 0 because I am not predicting any one. Now 0, how many ones are you predicting as 0? This is a 1 I am predicting as 0. So 1, 2, 3, 4. There are 4 ones which I am predicting as 0. In fact, all the ones I am predicting as 0. So 4 here. and there are 6 zeros which I am predicting as 0, so 6. So now you can compute the accuracy. This plus this divided by total, so 60%. Error is this plus this, so 40%. Sensitivity is how many ones out of total actual ones are you identifying. So you notice I am not identifying even a single one because I am predicting all zeros. So sensitivity is 0. Okay. Specificity is how many zeros out of all actual zeros are you correctly identifying. And if you see, since we are predicting all zeros, of course we will identify all the actual zeros also because we are predicting only zeros. So this will be 100%. Specificity will be 100% because we are capturing all the actual zeros. And precision will be again 0 because we are not identifying even a single one correctly. So both precision and sensitivity is 0. So this is the output of a baseline model. Now whatever machine learning model you build using any algorithm, logistic regression or whatever algorithm you use, it should be better than this algorithm. Okay. If it is not even as good as baseline, that means it is a useless model. It should be better than this baseline model is what you should focus on. So this is a benchmark for you. Whatever model you build should be better than this. Okay. Now let us move to the hands-on part and see how to run logistic regression in Python. Yeah, Prashant, you will have to remember what is precision. Just remember precision is same as sensitivity except the denominator. In sensitivity, the denominator is actual ones. In precision, the denominator is predicted ones. That's the only difference. Actual ones, predicted ones. Okay. So let me open this. So it is very similar to linear regression. Logistic regression is very similar to linear regression. Almost similar, just a few changes in the code. And in logistic regression also you will get a similar output. You will get a similar output which will give you the p-values and everything. So you will get the betas for each variable in the same way. You will get the betas, you will get the standard error, then you will get the p-values. And the same interpretation you will have now also. So again you will have to look at p-values less than 5% and omit the rest iteratively. Okay. And here also the null hypothesis is that beta is equal to 0 or the independent variable is insignificant. That is the null hypothesis. And the alternative hypothesis is that beta is not equal to 0. Okay. Or it is significant. And then you find the p-values. Now here we use a z-test to find the p-values in this case. In case of logistic regression, we use a z-test to find the p-values. And in linear, we use the t-test. Okay. We have already covered what a z-test and what a t-test is. So this is a case study which I'll be giving to you as a homework. So I'll not go into the details. I'll directly jump and show you how is a model run in logistic regression. Okay, so this ROC curve, we will talk about this tomorrow. but let me show you how do we run a simple logistic regression model. So guys, it is very similar to linear regression model. So remember, in linear regression, what we did, we imported linear regression here, right? From sklearn.linear underscore model, we imported linear regression. In this case, we will import logistic regression. As simple as that, okay? So we will import logistic regression this time, and then the same process. Pranay, you will, in the same way, you just look at the proportion of your historical data and you see which one is more, is 0 more or is 1 more, and you compare in the same way that we did right now. In the same way you will be doing in actual scenario also. So this is, I'm building a model here. Now this is one additional step. While creating the object, you will have to give this. Now what is this? Don't worry about this. You just memorize this. Okay, there's a reason why we do this, but you don't have to remember. And this is insignificant. Okay, so you don't have to remember this at all. So logistic regression, you create an object here. So log reg is the object now. And now again train test split I'm doing here also. So that is the same. Now you are fitting your data same way as you fit in linear regression. You take the name of the object, dot fit, you pass the training data, you pass the independent variables of training data, you pass the dependent variable of training data. Okay, and now your model is built. So this is where your model is finalized, your betas are finalized. Now you can predict using the model. So here I'm predicting on the trained data. First I'm predicting on the trained data, and then I'm computing the confusion matrix. So if you remember, we saw crosstab function when we started with Python. I think day 3 or day 4 we saw this. So crosstab function is used to compute such a matrix. So you write pandas dot crosstab, you give first the training data. Why did you give first the training data? Because in your confusion matrix you have training data on the left hand side, right? We have the actual values on the left hand side and the predicted values as column names, and that is why I am giving my training data first. So pd.crosstab, I give my training data first and then I give my predicted values, and I get my confusion matrix. So this is my confusion matrix. Okay, now from this I can compute my accuracy and everything. See, I have computed accuracy here, 70 plus 9 divided by total, so 86% is the accuracy. Okay, similarly I can predict on the test data also. This step was not required. You don't need to fit it again, so this is not required. So I'm predicting on the test data again. So previously I had predicted on the training data, now I'm predicting on the test data. Okay, so I have predicted on the test data and then I'm computing the confusion matrix on the test data. So this is the confusion matrix on test data. So these are the parameters. Okay, and I'm calculating the accuracy and everything. So accuracy is 75%. So you see, I got an accuracy of 86% on training data, but on test data I'm getting only 75% accuracy. So probably my model is overfitting here. My model is probably overfitting here. So I should check that. Okay, and the coefficients and all you can get using the same functions that you saw in linear regression. You write the name of the model and dot coefficient, you get the values of coefficient. These are the coefficients, these are the betas for different variables in the same order as you have declared your variables. So you see I have declared these 4 variables here, and in the same order I'm getting the beta values. These are the beta values for those 4 or 5 variables. And similarly I can get the intercept also. Intercept is beta naught. So intercept is this value minus 1.52. that is my intercept. So I've written that here. Comparing the accuracy of train and test, it looks like we have slightly overfit the data. We can try to exclude some variable to get a better fit and reduce complexity of the model. I have not done that. but I have mentioned it here. Okay, and then you can get the final equation from the above. To get the equation of the logistic regression, you can easily compute the equation now that you know your betas. So you know your betas, you can easily find the equation. Okay, ROC curve, we will talk about it later. We will talk about this tomorrow. No, Nitish. Then if you don't give Y train first, then you will have your actual values here. We discussed this in the previous class. And you will have your predicted values here. Yeah, so you will have your graph like this, and accordingly you will compute your accuracy, your precision, everything. That is the only difference. Your answer will be the same, but this is how you will compute. Your values will not be in the same order. So it is your wish. You don't show your confusion matrix to your stakeholders. You show your accuracy, sensitivity, precision, these values you show. So it doesn't matter in what way you are computing the confusion matrix. It's up to you. Okay. And again, now coming to the p-values part. So it is similar to what you do in linear regression. To compute the p-values, you again call the stats model API. So stats model API, you first add a constant. If you don't add a constant, beta naught will be 0. You don't want your beta naught to be 0, so you will add a constant, and then you will build your model again. So see here, we have not used OLS, we have used logit instead. Okay, logit stands for logistic response function. So instead of sm.ols, we are using sm.logit. Sm is the same as before. Sm is the same as before, but instead of OLS, we are using logit here, logit. Okay, that is the difference. Previously, we had used OLS, sm.ols. And then we will run this and again run the summary of this. Once you run the summary of this, you see the output is very similar to what you get in linear regression. So first you have the dependent variable. In this case, the name of the dependent variable was poor care. Model is logit model. Method is maximum likelihood estimate, MLE. This is the date and time when it was run. Okay, number of observations it is showing, and all these you can ignore. Okay, all these you can ignore. And now you can directly come to the coefficients. So the coefficients, see the p-values it is giving you. This is the p-value, and here is the z-value, which proves that this is coming from a z-test. In linear regression, it was written t here instead of z, because that was coming from a t-test. Yes, Tapan, there is an inbuilt function, but you use manually. You do it manually. There is an inbuilt function, which I have used here. Okay, but don't worry about this. First you use manually and understand how it is done. Remember the formula. Then later you can easily figure out how to do it using a function. And these things are not asked in interview, that how did you compute your confusion matrix manually or using a function. Okay, so don't worry about that. You focus on understanding the things and learning. Okay, so these are the p-values you see. The p-values are all less than 5% except one. So this pain variable has a higher p-value. So maybe I can run it once again and exclude the pain variable. The others are all significant, so I'll keep them. Okay, so this is the output of logistic regression, very similar to that of a linear regression, and it is in fact the same linear regression, right? So if you what we saw earlier was we take the same linear regression equation and we apply a function, the logistic response function, on top of it. So but it doesn't change much, it more or less remains the same, and that is why it is known as logistic regression, because we are taking a linear regression and applying the logistic response function on it. So it is more or less the same. The engine is the same with slight modifications. Okay, so I have done it here actually. So I have excluded the pain variable now. What I have done next is I have excluded this pain variable. Okay, and then I have run the model again. And now you see, now when I run it again, I get an accuracy of 80% on the test data also. So including the pain variable, it was overfitting the model, because see, this was insignificant. So this proves that if you have insignificant variables in your model, you should not include them, because this is what will happen. When I include pain and when I run, I get an accuracy of, how much did I get? 75% is what I got. Yeah, I get an accuracy of 75% on the test data. The train data is, see, 86%. Train data is 86%. Okay, test data is 75% with pain variable. When I remove pain variable, which is insignificant, the train data accuracy remains the same, but the test data accuracy, it improves. Previously it was 76%, now it becomes 80%. So now it is no longer overfit. It is still less than the train data accuracy. Train data accuracy is 86%, but 6% is okay. That is random variation. 6% up and down is doesn't mean that it is overfitting. So this proves that if you include insignificant variables in your linear regression or logistic regression models, it might overfit the data, and as a result of that, your test data accuracy might not be good. Okay. No, you don't have R square here, Tapan. You have something called a pseudo R square that you see here. You see a pseudo R square, which is like a R square for a classification case, but it is not popularly used. But there is something called a pseudo R square. Obviously, the higher the better. So you are getting 20% here. Okay, but it is not popularly used, so it's okay if you don't know this also. Okay, we use the other parameters that we discussed: accuracy, sensitivity, precision, etc. Now in this example, I have given equal importance to ones and zeros, and that is why I have not calculated the sensitivity, specificity, etc. I have only calculated the overall accuracy. So this is how you run a logistic regression model. I will share this file today itself. What we are not covering today is the ROC curve. So you just ignore this, okay? Ignore this section and move to the next one. Or maybe what I'll do is I'll delete these and then I'll send the files to you so that you don't get confused. Yes, same reason as we do for linear regression. In linear regression also we use the stats model just to see the p-values. Same here also. Okay, that will be easier for me. Okay, now let us talk about one more thing which I missed, which is interpretation of the coefficients. So interpretation of betas in logistic regression model. In linear regression we saw, right, it was easy. In linear regression, when you increase your x1 by 1 unit, your y increases by beta 1 units. Remember guys, that is what we saw. That was the interpretation of betas in linear regression. If you increase x1 by 1 unit, your y increases by beta 1 units. Okay, now how do we interpret in logistic regression? In logistic, since our equation is like this, our equation is not linear, so to make such an interpretation will be difficult. Let's say we have only one x. Now to make such an interpretation will be difficult because they are not linear. If it was linear, it was easy. So in this case, that is why we use the logit. Okay, So because when we are talking about logit, we are talking about the linear equation. So now you can say that if x1 increases by 1 unit, your logit increases by beta 1 unit. Okay, logit increases by beta 1 unit. So you will talk about logit now, because logit has a linear relationship, but you cannot talk the same about probability because the relationship is not linear. So you cannot say that if x1 increases by 1 unit, my probability of y will increase by beta 1 units, because they are not linear. So this is what you will have to interpret. Okay, is this clear, guys? Okay, now there is another interpretation, and that is with respect to sign, with respect to whether you have a positive beta or you have a negative beta. So what is that? Let us see. To understand this, we should look at the S curve that we saw. So remember the S curve, it looked like this. Okay, it never goes outside 1 and never goes outside 0. So it will never go below 0, it will never go above 1. It will always be in this range only, because it is probability. Okay, if you are doing something in logistic regression and if you are getting values above 1 or below 0, that means you have done something wrong. It is a probability, it cannot be outside 0 and 1. Okay, now this is what we saw, and here you have your linear regression line. Okay, now what does the sign of beta tell you? The sign of beta tells us that if your beta is positive, if your beta is positive, which side are you on, guys? Are you on this side or are you on this side? If your beta is positive, which side are you on? This left side or right side in this graph? Yes, we are on right side, right? If your beta is positive, you are on this side. You are on this side. And what do you have on this side? Guys, just a minute, okay? Please be on pause for a minute. Yeah, sorry guys, I had somebody at my door. Okay, so if what we were discussing about how the sign of beta influences, right? So if beta is positive, that means we are on the right hand side, so we are towards this side. So what do you have on this side? This side, what do we have? Guys, are you there? Yeah, you have 1 on this side, right? See, on the right hand side you have 1. So that means you have probability of y is equal to 1, or you say 1. So you have ones on this side. So this means that positive values of beta, positive values of beta results in 1. Okay, results in ones. Similarly, negative values of beta, negative values of beta results in zeros. Because if you go towards this side, negative value of beta means you will be on the left hand side. So you will be closer to the zeros. Here you have the 0 points. Here you have the points which are ones. Okay. So that means negative values of beta results in zeros. Positive values of beta results in 1. Okay. So this is how you interpret with respect to sign. So for example, one example, so you will understand this once you are doing something yourself. So let's say you are trying to predict whether somebody will default on their loans or not. Okay. And you have, let's say, age. So what do you think? Will age have a positive beta or will age have a negative beta? Let's say age has a positive beta. If age has a positive beta, that means with higher age, your probability of defaulting increases. Okay. If age has a positive beta, it would mean that with increasing age, your probability of defaulting increases. Okay. But on the other hand, if age has a negative coefficient, that means young people are less likely to default on their loans. This is what it would mean. Okay. I think I have that mentioned here somewhere. The interpretation part, yeah, it is here. Interpretation of the model. So this means that, so here there are some variables which are particular to this case study. So you will not understand now. Once you go through the problem statement, you will understand. Okay. But whatever I discussed, that is how it is. If it is positive, it pushes you towards the probability of 1. If it is negative, it gets you closer to the zeros. Out so far, guys. I know whatever we discussed was pretty new to you, so you will need some time to revise it. But trust me, it is easy. It is easy because you saw very few new things. Most of the things are taken from linear regression. The p-values, the overfitting concept, everything is as you have in linear regression. The only new things you got was the logistic response function, the concept of odds, the interpretation changes now. So these are the only new things which you have in logistic regression, and obviously how you evaluate your model, that also changes. Otherwise, more or less, it is the same model. That means that if if you get a positive coefficient for age, let's say you run a logistic regression model where your dependent variable is whether somebody will default on their loans or not. Okay. Whether somebody will default or not. So this means that default is 1 and not default is 0. Okay. By default, I mean they will not pay their loans. Okay. So these are the bad guys who default and these are the good guys. Don't see the not here. These are bad, these are not bad. That means the good guys. And let's say now if you get a positive coefficient for age. For age, you have a positive beta. What does this mean? This means that, so remember the S curve. It looks like this, where this is the default guys and this is the good guys who don't default. They are here. And these are the bad guys. So if your beta is positive now, that means with increasing age, you tend to default more. Okay. This is what it tells you. If your age has a positive coefficient, whereas if your age has negative coefficient, negative means the higher the value of beta, now you will go towards this side because it is negative. So that means with increasing age, you will not default if it is a negative coefficient. Okay. So this is the interpretation with respect to sign of beta. And obviously if the age increases by 1 unit, the logit increases by beta units. Okay, not the probability. The probability does not increase by beta units. Okay, the logit increases by beta units, because beta might be, let's say, 4. Beta can be, let's say, if beta is 4, and if probability is, let's say, 30%, and if you increase the probability by 4 times, it will already cross 1, which is not possible. So the logit increases by beta units, not the probability. Okay, this is all the theory on linear regression. Now, one thing, just to give you a heads up, I will not cover this today, I'll cover this tomorrow, but just so that you don't get confused once you look at the solutions of the case study. So we are always talking about the probability. Remember, everywhere we are talking about probability, right, guys? In the equation also we have the probability. But what I am showing you on the confusion matrix, if you see the confusion matrix, I am showing you 1 and 0, right? I am not showing you a probability here. I am directly showing you 1 and 0. But what the model is predicting is a probability. It is not showing you ones and zeros. So that means you can have numbers like this. But how do we convert these numbers to 1 and 0? We'll have to convert these numbers to ones and zeros. Only then you can calculate the confusion matrix. So how do you convert a probability to 1 and 0? For that we use a threshold. Okay. For that we use a threshold. A threshold is just, let's say, for example, 0.5. So what you will do, whatever probability is below 0.5, you give it as 0. Whatever probability is above 0.5, you say that it is a 1. So now you have converted your probability to ones and zeros, and that ones and zeros you take to compute the confusion matrix. Because you cannot compute confusion matrix from probability. You need ones and zeros. So to convert the probability to ones and zeros, you use threshold. Whatever is above a threshold, you take as 1. Whatever is below a threshold, you take as 0. So the probability basically means that, let's say if you get a probability of 0.1, this means that this person has 0.1 probability of defaulting. If your dependent variable is default, it means that this particular row or this particular person has 10% probability of defaulting. Okay, so obviously 10% is very less, so you will say that he will not default. You will say he is a 0 for default. But if somebody has 90% probability of defaulting, you will say that he will default. You will give a 1 to him. So how did you do that? You had a threshold of, let's say, 0.5. So whatever was below 0.5, you said he is 0. Whatever is above 0.5, you say he is 1. So this is how you convert your zeros, you convert your probabilities to ones and zeros. Okay. Tomorrow we will see another phenomenon where we use ROC curve, where you use a ROC curve to do that. Okay, that is what is shown here. This curve that you see here, that is the ROC curve, which is used to do that. But right now you just assume that we will take 0.5. We will take 0.5 and we will convert probability to ones and zeros. Why 0.5? Because it is in the middle. That's what, Pranay, that says the probability. The S curve that you see, it doesn't give just ones and zeros. It will give you probability. So this is the 0.5% probability. So if you assume a threshold of 0.5, this means whatever is above this you are saying as 1, whatever is below this you are saying as 0. Okay, this is what it means. Whatever is above this is 1, whatever is below this is 0. If you take 0.5 as the threshold. In some scenarios we will discuss tomorrow where we will not take 0.5. We will take something lesser, maybe 0.2. we will take something lesser, maybe 0.2. So whatever is above 0.2, we will say 1. Whatever is below 0.2, we will say is 0. Okay. Again, we will again discuss about the cancer thing. So even if somebody has 20% chance of having cancer, you will still say that he has cancer so that he goes for a treatment. Okay. So that is where you vary the threshold depending on the business requirement, depending on the severity of your outcome. You vary the threshold. You don't always keep it 0.5. So we will discuss about such scenarios. Okay. But right now you just know that we use 0.5 as a threshold, and then using that threshold we convert our probability to ones and zeros, and using those ones and zeros we compare with the actual using a confusion matrix, and we get the output. So this is what is shown here. So first is the initial analysis that we do, the EDA part, what Shubham was asking. So initially we do a lot of analysis. We try to understand our data well. How is it related to other data? We try to find multicollinearity, because multicollinearity is an issue here. So this is where I'm trying to find multicollinearity in my data, because I don't want two variables which are highly correlated to be added in the model. Two variables, by two variables I mean the two independent variables. So and then I have started my model building. No, that was just a hit and trial, Pradeep. That is just a hit and trial. You try 10 things, one or two of the things will work, the other will not work. Okay. This ROC curve, don't worry about this. We will discuss this tomorrow. So you just skip this portion. And the remaining is I have given enough comments here. So if you read, you will understand this. Okay, so that is all I had for today, guys. If you have any questions, I can take it, or I can go for a revision. I don't think we will need a extra hour of class today. Okay. So maybe in another 15-20 minutes we can wrap up. Yes, guys, any questions do you have from today's class? So probably tomorrow you will have more questions because you would have revised by then, and then you would have questions, because right now the things were pretty new to you. Okay, Kishwar has a question. In linear regression, how do we decide which is dependent and which is independent by looking at the data? No, Kishwar, you don't have to decide that. Your stakeholder will tell you that. Okay, that the problem statement will mention that. So you don't have to decide that. The business
Guys, you should be able to hear me now, right? Okay. No, Pradeep, it was not moving by itself. I was checking whether you guys can see the screen or not. I too have a small screen here which shows the audience view. I was checking whether it is moving or not by doing that. Okay, so let's do a revision, guys. Okay, I think we had a few questions. Kishwar, so your question is answered, right? You don't have to worry about which variable being dependent and which others being independent. So that will be told to you. Okay. So your dependent variable will be told to you, and whatever else is there is the independent variable. Pranay, you don't need to worry a lot about stats and probability. Stats, I've already covered whatever is required. So beyond this, if you go, there is an entire world in stats. Okay, you will need 3 years, 4 years. People do bachelor's, masters, and even PhD in statistics. Okay, so there is no end there. But whatever is required for data science, I'm covering here. So first try to be very comfortable in these things, then you can move to more details. And trying to be comfortable in these things itself will take you maybe 6 months to a year. So after that, maybe you should ask this question that what else should I study in stats? Okay. No, Pranay. This is all I have. There is no more handwritten notes that I have made. Okay. I have a few books which are very good, but they cover a lot in stats. So I would not recommend that to you guys now. Yes, Keshwar, so that is not possible. You cannot do a univariate analysis if you have 100 variables. So that is where your business understanding comes into picture. If you have a good business understanding of the problem, you will only do a univariate analysis on the variables which you think are important, not on all the variables. Okay, so that is where business understanding comes to your rescue. Yes, Pradeep, you can share that book. I will share once your course completes, guys. I will share a few books with you guys, which will be very small books, some 300, 400 pages books, so that you can refer, but not now. I don't want you guys to go to the book and not focus on what I'm teaching. Okay. So once the course completes, I'll share some books for further study. Some books and some online courses also I will share. Okay, so let's start the revision and finish today's class, guys. So what did we see today? We started with our first classification algorithm, which is logistic regression. Okay, our first classification algorithm, which is logistic regression. Yes, it is on. So what is logistic regression? In logistic regression, we take the same linear regression graph, linear regression equation, and we apply a function on top of that. Why do we apply a function? We apply a function so that our output is only between 0 and 1. Because we have seen in logistic regression, since it is a classification case, the output is only 0 and 1. So we cannot have output outside this range. If you get negative values, if you get positive values, let's say 10, 15, 100, 1000, it will become very difficult to interpret that, because your output is only 0 and 1. And that is why we don't use linear regression, because linear regression, if we use linear regression, is an infinite line. It doesn't have any bound. So if you use a linear regression, the output will be anything. It can be negative, it can be positive. So it will become very difficult to interpret such a output. So we apply a function on top of linear regression line, and then we get logistic regression. Now this function is known as logistic response function. Okay, and it looks like this. Once you apply that function, what you get is a probability. And remember, this is a probability of y is equal to 1, not probability of y is equal to 0. Okay, this will be 1 plus e to the power minus beta naught plus beta 1 x. This is your logistic response function. We also saw the concept of odds. The concept of odds is, the formula for odds is probability of 1 divided by probability of 0. If you put this equation here and if you solve it, you will get e to the power beta naught plus beta 1 x. Okay, and then if you take log of odds, if you take log of both sides, you will get beta naught plus beta 1 x. Log of odds is also known as logit. So logit is equal to beta naught plus beta 1 x. So this is what we get. This is the final equation. Now, how do we get the values of beta in logistic regression? So just like ordinary least square, we have maximum likelihood estimate in logistic regression. It starts with random values of beta. It starts with random values and then compares prediction with actual. Since it is random values, obviously it will not match, so it will change the values. It will keep changing, a lot of iterations will go on, and finally it will get some betas, which gives you a result which is very close to the actuals. So it will fix those betas. Once you have those beta, you have this equation. So that is the maximum likelihood estimate. Then we learned about the interpretation of the equation. So we saw the S curve here. This is the equation of logistic regression. Guys, you should be able to hear me now. The power returned and there was a fluctuation in voltage, which is why the connection was lost. Okay, so let's finish this before the power goes off again. There's a huge storm kind of a wind going on in this area, so let's quickly do this. Okay, yeah. So this is what we have. So this is your probability of y is equal to 1. No, Bilandur. Okay, so this is, and this is your beta naught plus. Okay, so what we saw is if you get a positive coefficient, if you get a positive beta, that brings you closer to the probability of y is equal to 1. Okay, because this is the 1 line, this is 0 line. So positive beta results in ones. Positive beta results in 1 and negative betas results in probability of y is equal to 0, or you can say zeros. Okay, so this way you can interpret your coefficients using the sign of the coefficients. Of course, using the units of the coefficients also you can. So using the logit function that we saw. So if your x increases by 1 unit, your logit increases by beta 1 units. This is another interpretation of logistic regression. We saw the two assumptions of logistic regression. One assumption again coming from this equation, that your independent variable should have a linear relationship with the logit or log of odds. So log of odds and independent variables should have a linear relationship. This is one assumption. The other assumption is that no multicollinearity. This is same as linear regression. There should not be any multicollinearity. So these are the only two assumptions in logistic regression. What else did we see? Yes, guys, what else did we see? We saw baseline model. What is a baseline model in classification? So in classification, a baseline model always predicts the mode. Okay. Mode is whichever is more in proportion, ones or zeros. Whichever is more in proportion, mode will predict that. Yeah, we covered overfitting and underfitting. So overfitting is when your training accuracy is greater than your test accuracy. This happens because you have built a overly complex model. Overly complex model which does not generalize well. Which does not generalize well on unseen data or test data. Okay, that is where you know that you have overfit, and it should be greater than, there should be greater than 6% difference, 6 or 7% you can say. Just because it is 3 or 4% less, that doesn't mean it is overfitting. Of course, there will be some random variation, but if the variation is beyond 7%, that means that the model has overfit. So we should be careful and try not to overfit the data. So how do we avoid that in linear and logistic? In linear and logistic, we avoid overfitting by taking fewer variables. We take fewer independent variables. Okay, so to avoid overfitting, remember the graphs that we drew. To avoid overfitting in linear and in logistic, we use fewer variables. Okay, or we use only significant variables. We drop all the insignificant variables. This way we can avoid overfitting. Okay. Anything else? I think that is all that we covered today, right, guys? So, and the hands-on part is pretty simple. I'll send the codes right away. So go through the codes and go through the videos also once before tomorrow's class, guys. Okay. Please go through what we learned today at least once before tomorrow's class. Then you will understand better, because tomorrow we will go into more details. So if you have not followed what was done today, you will not understand what is happening tomorrow. So please understand today's material by tomorrow morning. Okay. Just understand the logic. Even if you don't remember the equations and everything, that is okay. But the logic and all should be clear, that this is why we are doing what we are doing. Tomorrow we will see how do we decide a threshold, or how do we convert the probabilities that we get into actual zeros and ones. So we saw today that we usually use a threshold of 0.5, but can we take any other threshold? How do we decide the threshold, what threshold to take? How does it change depending on the business scenario? So all those things we will see tomorrow. So we decide the threshold from a ROC curve. So ROC curve we will see tomorrow, and we will see the hands-on of how to generate the ROC curve in Python, how to read the ROC curve, and we will see one more accuracy parameter for classification, which is called area under curve. So these things we'll be looking at tomorrow. Okay, guys. So that is all I had for today's class. Yes, Amar, I will share the video ASAP. Okay. Okay, guys. Thanks everyone. I'll see you tomorrow. Remember, tomorrow also the class timing is 8:30. Okay, bye guys.